For the first part of today, we're going to start looking more into the true meaning of what a chemical formula means. And today's lecture as a whole is going to start to take what we've learned about atoms and bonds and compounds and bring it into the real world. Because at this point, we've talked only about theory. And you can talk about one atom does this, well, another atom does this, and the two come together and bind to each other. But that's kind of working in a fairy tale way, right? That's not real world. We're assuming that happens, but we can't see that. So what does a chemist do when a chemist is in the lab? We're going to start working our way that way. First thing we're going to look at is something called percent composition. This is easy, okay? Every time someone puts an equation up here, and you first look at it, it looks difficult. But percent composition is easy. All it tells us is what percent of a compound is made up of each element. And in order to do that, in order to find percent of an element in a compound, you take the mass of that element and you divide by the total mass of the sample or the total mass of the compound. Okay? So let's say we have a rock that's made up of element A and element B. The whole chunk is 100 grams, and there's 30 grams of element A. What's the percent of element A? 30 divided by 100, 30%. That's what this is. Okay? Just take how much one element weighs, divide it by the total weight. It's just telling you what percent of the total mass comes from a specific element. The mass of the element divided by mass of sample times 100%. So here is an example. We have a mineral called chalcopyrite. It is made up of copper, iron, and sulfur. It gives us masses of each element. This is what is the mass percent of each element. So if I want to find the percent mass of copper, what do I do? In someone's extra credit question, they said, if I write on the right side of the board, you can see it better.
Yeah.
Did you mean the right side of the left side or the right side?
This side.
This side, so here.
That was me.
Okay. Okay. So I'll try to stay over here as much as I can. So we got 1.27 grams over what?
Total.
The total. So what is it?
3.67
3.67 grams. So if you just added 1.27 plus 1.12 plus 1.28, the total is 3.67. And when you do that, what do you get? 0.346, which is what? How many percent? 34.6%. How many sig figs? 3. We need 3 sig figs, which we have. Now we got to do the same thing for iron. So we get 1.12 divided by 3.67 is what?
0.305, which is
0.05, 30.5%. And then finally we do sulfur, 1.28 divided by 3.67 equals 34.
Actually, if you round it up, it's
34.6% copper, 30.5% iron, 34.9% sulfur. And hopefully, if you add these up, that adds up to 100%. Because all your percents have to add up to 100. If they don't, you either did the math wrong or there's an element missing. So this is taking this and looking at it in a pie chart. So all the pieces have to fit together to equal 100%. Here we have a little bit different question. It says we have a copper compound that weighs 1.63 grams, 1.30 grams of copper. It says the other element in the compound is oxygen, but it doesn't tell us how much oxygen is in there. We have to find the percent composition, which means the percent copper and the percent oxygen. How do you want to do this?
Well, you would take the percentage, you take the percentage of the copper and then subtract 1 to do the decimal.
Samantha, what'd you say?
Solve for copper and subtract that decimal point.
Right. And so if you remember that they have to add up to 100%, if you find a percent copper, the rest of it has to be oxygen. So we're going to find the percent copper. We've got 1.30 grams of copper divided by the total mass is 1.63 grams. What is the percentage of that? 79.8% copper. So percent oxygen equals 100 minus 79.8, which equals 20.2%. So even though we weren't given the mass of oxygen, we could find the percent oxygen. And now that we have the percent oxygen, we could find the mass of oxygen if we needed to, but it's not asking. You can only do the subtraction method if there's only one element you don't know the mass of. So if it said the copper compound weighs 1.63 grams, it has 1.30 grams of copper, the other elements in the compound are oxygen and sulfur, what's the percent composition? You don't know. You would know that the total between oxygen and sulfur is 20.2, but you have no idea the ratio between the two.
So you just say it can't be proven or can't be.
You would say that, but you would also never be asked that, because it's an impossible question. So the way I guess I did it here is rather than subtracting at the end, once I got the percent, subtracting 100 minus the percent, I said, well, if the whole thing weighs 1.63 grams and 1.3 is copper, there must be 0.36 grams of oxygen, and then did the division. So they both get you to the same place in the end. Okay. We're going to move on to the mole. And the mole is a very simple concept. It is going to haunt you the rest of the semester until it clicks. Okay? For some of you, it may never click.
Yeah.
But it is really simple. Okay? So what a mole does is it allows us to count something that comes in very, very large numbers. So we're going to take the number of atoms or the number of molecules that we have, and we're going to say how many of them we have. But you don't want to write a number that's that big, and you don't want to count that high. And so So instead of counting individual atoms and molecules, we count by what we call the mole. And a mole is 6.022 times 10 to the 23rd particles. When I say particles, I mean anything that you want to count. It could be atoms, it could be molecules, it could be desks, it could be people, it could be eggs. It's anything you want to count. Okay? So 1 mole of carbon equals 6.02 times 10 to the 23rd carbon atoms. A mole of hydrogen sulfide, H2S, is 6.022 times 10 to the 23rd H2S molecules. A mole of copper 1 oxide equals 6.022 times 10 to the 23rd Cu2O units. And if you're counting moles, a mole of moles is 6.022 times 10 to the 23rd little fuzzy things. Okay? We abbreviate mole, M-O-L. It saves you 1 letter. But if you write it 10 times, it saves you 10 letters. So you can abbreviate mole, M-O-L. Okay? This number, 6.022 times 10 to the 23rd, is called Avogadro's number. Avogadro was the guy that discovered this. I think I forgot to look it up last time. I meant to put a picture in. If you think of it, look up a picture of Avogadro. He's a really creepy looking dude. Okay? When you see his picture, he reminds me of Rumpelstiltskin from the Shrek 2 or Shrek 28 or whatever that version of that movie was. Okay? So a mole is this really weird number, but think of it like a dozen. So a dozen is 12 of something, right? You can count how many dozen of an object you have. If I put 24 things up here and asked you how many dozen I had, every single one of you would get it right. A mole is the same idea, it's just a much more difficult number that you're counting by. It's 6.022 times 10 to the 23rd instead of 12. So if I had 12 items up here, how would you figure out how many dozen I had? You divide it by 12. You count how many I had, divide by 12. You do the same thing with a mole. In order to figure out how many moles you have, you take the total number that you have and divide by 6.02 times 10 to the 23rd. Yeah? This is the American Chemical Society's mascot. He shows up to conferences. If you pay him enough, he might show up to your birthday party. Any fans of the comic XKCD? Anyone heard of it? It's a really nerdy cartoon. Okay. The guy asks, in addition to just cartoons, he has these what-if things and says, takes scientific principles and applies them to real life and says, what would happen if? Somebody asked him, how big would a mole of moles, being rodents, be? And so that is how big a mole of moles would be compared to the moon. 6.02 times 10 to the 23rd rodents is about as big as the moon. That tells you how many 6.022 times 10 to the 23rd is. Think about it. Times 10 to the 9th is a billion. 10 to the 12th is a trillion. This is 10 to the 23rd. We're talking about a really, really, really large number. We need a really large number, though, in order to go from the subatomic, the molecular level, to the real world level. Because atoms are very, very small. So if we have an amount of a substance or a compound that is workable in real life, the number of atoms that we're dealing with is enormous. And we don't want to use these gigantic numbers in all of our calculations. We want to use reasonable numbers. 1, 2, 5.5, things like that. And so the mole allows us to work in the microscopic world using real world numbers. where that weird number comes from is that he figured out how many atoms of carbon it takes to weigh 12 grams. And so carbon-12 has a mass of 12, and so he figured out if this number, originally we said that's atomic mass units, right? When we're dealing with one atom, those are atomic mass units. He made it convenient and he said, let's figure out how many atoms it takes so that we can use the same number as grams. And so, take 6.02 times 10 to the 23rd carbon atoms to weigh 12 grams. And then that same little measurement got applied to all of them. And so from now on, we can look at these numbers, these weights, and they'll also be grams. Not just AMUs, there'll be AMUs at the molecular level, when we're talking about one molecule or one atom. But when we're talking real world, in the moles, these are going to be grams. To give you an idea how much a mole is, this is a mole of several different elements. So it is like kind of a small handful amount of a mole. So it's a realistic amount. It's an amount that we can use in lab. This is where people start to struggle a little bit. We can take the term mole, and remember to think of it like a dozen. We can apply it to anything we want to. So if we have a mole of H2S molecules, how many sulfur atoms are in that mole of H2S? 6.022 times 10 to the 23rd. Because we have 6.022 times 10 to the 23rd molecules, and each molecule has one sulfur atom. And so 6.022 times 10 to the 23rd times 1 is how many sulfur atoms we have. How many hydrogen atoms are there? 6.022 times 10 to the 23rd times 2. Because for every molecule, there are 2 hydrogen atoms. So if you're going to take that, and you're going to break it up in the individual atoms, you're not going to have twice as many. So, how many total atoms are in H2S? 3. There are 2 hydrogens and a sulfur. What is a third of a dozen? 4. Okay? So imagine we have a dozen eggs. And in that dozen eggs, we have 2/3 red, 2/3 green. How many? Did I say 2/3? 2/3 red, 1/3 green. Okay. You're able to tell me, say if I have a dozen eggs and 2/3 are red, 1/3 are green, you can very easily tell me how many red ones I have, 8, and how many green ones I have, 4. This is the same thing. Because there are 3 total atoms and 2/3 are hydrogen, you can just take the 2 and multiply it by, I don't know what I'm doing. I confused myself. It worked when I started, and then I went down the rabbit hole, and it just went on. Let's start back at the beginning. If you have H2S, okay, you have 2 hydrogens for every 1 molecule. Let's not make it more difficult than it is. If you have 2 hydrogens for every molecule, and you have 1 dozen molecules, you're going to have 2 dozen H atoms. If you have 1 dozen H2S molecules, and then you have 1 atom of sulfur per molecule, you still have 1 dozen sulfur atoms. Okay? said we're going to start looking at these numbers as grams. They're not just grams. They are grams per mole. So that is the unit. Grams per mole, and we call that the molar mass, meaning it is the mass of a mole of that element. So, a mole of boron weighs 10.81 grams. A mole of beryllium weighs 9.01 grams. If I have 2 moles of hydrogen, how many grams do I have? 2.02. 1.01 times 2. Each mole weighs 1.01, and I have 2 of them. And so I add 1.01 plus 1.01 is 2.02. If we want to find the molar mass of a more complicated molecule, like CO2, all we do is we add up the masses of each atom in there. So the mass of carbon is 12.01, and there's just 1 carbon in CO2. So it's 12.01 plus 2 times the mass of oxygen. Oxygen is 16, there are 2 of them, there's 2 times 16, add it together and you get 44.01 grams per mole. A mole of carbon dioxide weighs 44.01 grams. 2 moles of carbon dioxide will weigh 88.02 grams. 44.01 times 2. What is the atomic mass of a hydrogen? 1.01. What is the molar mass? 1.01. What are the units here?
Atomic mass.
Atomic mass units, AMUs. What's the unit here? Grams per mole. So we said oxygen was 16, so 16 here. Sodium is what? 22.99. So it's same over here. Calcium chloride. How do we find the atomic mass of calcium chloride?
You add the mass of calcium and 2 times the mass of chlorine.
6 oxygen.
And then 6 oxygens. So we're going to start with calcium. How many calciums do we have?
1.
Just 1. 1, and the mass of calcium is 40.08. And then we have chlorine. How many chlorines do we have? We have 2. We have 2 of these units. There's 1 chlorine per unit, and so there are 2 chlorines. We're 5. And then oxygen. How many oxygens?
6.
We have 6. There are 3 oxygens for every one of these, and we have 2 of them. So 2 times 3 is 6. Oxygen is 16.0. So now we multiply them, we get 40.08. And this is 71. And then what's 6 times 16?
96.
When you add them up,
107.08.
107,
207.
207.08. What's my unit?
Grams per mole. Or
Depends on which column we're doing, right? The same numbers when they go in both columns. If we're on the atomic mass column, it's AMU. If we're on the molar mass column, we're grams per mole. In terms of sig figs for this, what I would suggest doing is, in this case, they round everything 2 decimal places, and so I would just put your answer to 2 decimal places. You're not going to be graded on sig figs of molar masses like this. Okay.
I got 206.9.
That's 35, 0.45 times 2 is.
Yeah, that's not exact 370.
Okay.
Yours is more accurate than mine. So we got 207.08. What about water? Can you do that in your head? What's hydrogen? 2.02 plus 16. 18.02. I personally would just round hydrogen to 1. That's 2 plus 16 is 8. Sodium chloride, you got 23 plus 35.45. Does this make sense? It's the same exact thing we were doing for molecular weight. It's just in the end, your unit is grams per mole instead of AMs. Okay. This is a mind-blowing thought question that everyone always hates. Everyone always hates these thought questions. You have a mole of copper and a mole of gold. Which one weighs more?
The one that was
Here's something that's the same. And I'm going to say copper. How many say gold? How many say they're the same?
You can have a pound of feathers and a pound of bricks.
A pound of feathers and a pound of grapes, you said?
Bricks.
Bricks. I was going to say, I don't think that's how that phrase normally goes.
Still a pound of it.
Yes, a pound of bricks and a pound of feathers is the same. But these are moles. That tells us how much one mole weighs. So it's basically saying, does a dozen feathers weigh the same as a dozen bricks? No. So a mole of copper weighs 63.55. A mole of gold weighs 196.97. So the gold weighs a lot more. So that's not even what the question was asking me. Nobody pointed it out. I made up my own question. Which contains the greatest number of atoms?
Yeah, so they're the same.
They're the same. Yes.
We were right.
That's Avogadro's number.
Yes. Keeping you on your toes. Not confusing you, keeping you on your toes. So the question on the board, not what came out of my mouth, the question on the board said which contains the greatest number of atoms? A mole of copper or a mole of gold? The same. It's like saying which has more eggs? A dozen of Publix eggs or a dozen of Winn-Dixie eggs? Unless somebody stole one out of either of them, they both contain 12. Okay?
It just weigh different. It just weigh different to equal the same amount of
Yeah, the mass is
Yeah.
different.
And so if you said, which has more eggs, a dozen large eggs or a dozen medium eggs? It's the same. But the dozen large eggs is going to weigh more. Yeah.
Can you upload the PowerPoint with the answers on it?
I
Like, for the
pur-
one that you
I purposely leave them off. And so that you have to pay attention and write them.
I don't like that.
Just, it's like, sometimes I have time.
Which contains more atoms? A gram of copper or a gram of gold?
gram.
Okay, copper and gold. How many say copper? How many say gold? How many say they're the same? Who wants to defend their answer?
Defend mine, but I'm not like totally sure.
Okay.
I thought of it as in like a gram. It's a weight unit. It's not a number of atoms like Avogadro's number. So a gram of copper, since copper weighs less, you'd have to have more atoms to equal the same amount.
Correct. You have a gram of copper and a gram of gold. Each copper atom weighs less. Each individual atom weighs less. And so to add up to a gram, you're going to need more of the copper atoms than the gold atoms. You can also look at it in terms of how many moles of each you have. So before, we were going from moles to grams. We kind of looked at that. How do you think you can go the other way? If you have grams, how can you figure out how many moles you have?
Times
It's even simpler than that. How much does 1 mole of copper weigh? 63.55. Let's go the other way. If you have 63.55 grams of copper, how many moles do you have? 1. How did you figure that out? Mathematically.
Oh, you divide it by its mass.
You divided it by the mass. You said 63.55 divided by 63.55 is 1. I have 1 mole of copper.
So you would just divide 1 by its atomic mass.
Correct. Divide 1 gram of copper by the atomic mass of copper, or the molar mass of copper. That will tell you how many moles of copper you have. It's a small number. If you do the same thing with gold, though, you're going to divide by a much larger number. And so you're going to get a much smaller answer. Which means you have a greater percentage of a mole of copper than you have of gold. Which means you have more atoms of copper. So this is exactly what we just did in our head. We're converting between grams and moles. So the first one up here is converting 10 grams of CO2 to moles. So we're going to use dimensional analysis. Okay? When I do this conversion, I use the crosses in the boxes. Okay? That's what we're going to do up here when I do that. But in the slides, they do it with these fractions. From looking at the work of some of you prefer this way. It doesn't matter. You get to the same answer in the end. And so we're starting with 10 grams of CO2. We have grams of CO2. Grams of CO2 has to be down there. And 44.01 grams of CO2 equals 1 mole of CO2. Your dimensional analysis is set up. You're done. You do the math. You end up with 10 times 1 divided by 44.01, and you get 0.227. Make sense?
Just a conversion.
Just to convert. So let's do the next one. Yeah. This time we're going to go the other way. We're going to go from moles to grams. So we are starting with 0.50 moles of CO2. I'm going to use dimensional analysis. What unit is going to go down here? Moles of CO2. This gets copied down here. What unit do you want to put up here? Grams of grams of CO2. We're going to go from moles of CO2 to grams of CO2. Now the slightly more tricky part is the numbers. What number do you want to put here?
You're going to want to add the carbon. Oh, for that you're putting 1.
We're just going to put 1. It's easier than you were making it. So it's 1 mole of CO2 weighs how much?
And that you would add the carbon.
You're going to add the carbon plus 2 oxygens. It was just on the 44.01. If you add it up, 44.01. So you get 0.5 times 44.01, 22.005 grams of CO2. How many sig figs? 2. 0.50 is 2 sig figs, so it's just 22 grams of CO2. So whether you're going from grams to moles or moles to grams, the only thing that changes is you can flip this how you need to flip it. has the wrong number of signals.
This,
So here we converted 10 grams of oxygen to moles. Notice that it is O2, because oxygen is one of the diatomic elements. And so if you're looking for the molar mass of O2, it is 32. It's not the 16 that's up there. Because there's 2 oxygen atoms in that molecule. 16 plus 16 is 32, so it's just 10 divided by 32, 0.312. Now we're going to move into the 6.022 times 10 to the 23rd. And this is going to trip some people up. So we can go, convert between grams and moles and particles. You have to remember that 1 mole is 6.022 times 10 to the 23rd particles. That is a conversion factor. We can use that in dimensional analysis. We can put 1 mole on top and 6.022 times 10 to the 23rd on the bottom, or we can flip it, put 1 mole on the bottom, 6.022 times 10 to the 23rd on the top. This is kind of a flow chart for conversions, and it tells you what your conversion factor is, so you can go from any of these to anything else on that. So this question is asking us the mass of magnesium chloride that contains 6.022 times 10 to the 23rd chloride ions. Okay? We're going to do this with dimensional analysis. You might be able to do this in your head using some logic. But if you're not comfortable with that, dimensional analysis is the way to go, because the units will lead you from beginning to end. Okay, so that's how we're going to do it. So what number am I going to start with? There's only one number I have to start with, right? 6.022 times 10 to the 23rd chloride ions. So, using dimensional analysis, I got to go somewhere. What units have to be here? Chloride ion. It has to be that. Now, from this point, there are a couple different paths we can take. That'll lead us to the same place in the end. Which one do you want to take? What do you see as the most obvious route? That's not going to get us where we need to go.
You would do could you do the atomic mass of that? And then 1 mole?
My suggestion is let's get out of these gigantic numbers. I would get into the realm of moles as soon as possible. Get into more realistic numbers. So if I want to figure out how many moles of chloride ions that I have, how can I do that? I want to go from chloride ions to moles of chloride ions.
1 on top and then the 6.022.
1 mole of chloride ions equals 6.022 times 10 to the 23rd chloride ions. I'm now in moles. Dimensional analysis, so what unit has to go here?
Oh, that's why.
Moles of chloride ions. Where are we trying to get to in the end?
Grams.
Grams of what?
Just the chloride.
Yeah, just the
Okay.
chloride.
What is the question asking us
Oh,
for?
magnesium chloride.
Grams of magnesium chloride, not chloride, magnesium chloride. So if we can figure out how many moles of magnesium chloride we have, then it's easy to figure out how many grams of magnesium chloride we have. So I'm going to convert from moles of chloride ion to moles of magnesium chloride. What's my conversion factor here?
1 mole.
How many chloride ions are in a magnesium chloride? 2. Every 1 mole of magnesium chloride has 2 moles of chloride. Because there are 2 chlorines in MgCl2. So now we just have the last conversion, 1 mole of MgCl2 weighs a certain amount, and it tells us 95.21. I'm going to button, if you do the math, 47.60 grams of magnesium chloride.
The 2 they can cancel each other out.
Say it again?
The 6.02 on the top and diagonal ones can cancel each
Right.
other out. These are the 2
Right.
numbers.
So these 2 big ugly numbers cancel each other out, they just go away. So now you've got 95.21 divided by 2. From here, we're going to move on to something called an empirical formula. When we write a chemical formula, it can either be in empirical formula format, or it can be in molecular formula format. And essentially the difference is empirical formula is simplified. Remember when we were doing ionic compounds, we said they always had to be simplified, right? If we have calcium sulfate, calcium has a 2+ charge, sulfate has a 2- charge. If we swap them, we get Ca2, SO4, 2, but that's not correct, we said. You have to simplify it, CaSO4. This is simplified. That is an empirical formula. For ionic compounds, we always use empirical formulas. You didn't realize you were doing that, but you were, because you always checked whether it could be simplified. For a covalent or a molecular compound, we can have molecular formulas. Because those we didn't simplify, right? If we had C2H6, we didn't simplify that to CH3. We left it C2H6. And so C2H6 is a molecular formula. It can be simplified, but it has not been. So the empirical formula is the smallest whole number subscripts. It's simplified, and it just tells us the ratio of one element to another. So if I have CaSO4, that means that there's 1 calcium for every sulfate. It doesn't tell me that I have 1 of these and 1 of those. It means I have 1 calcium for every 1 sulfate. It could be 2 and 2. It could be 5 billion and 5 billion. A molecular formula tells you exactly how many of each atom are in a molecule. If that happens to be simplified, then that formula is both the empirical and the molecular. So something like C2H6 is going to have a different molecular formula than it will have empirical formula. If you want to simplify that, what would you simplify it to? CH3. You divided 2 and 6 by 2 to get C1H3. So this is the molecular formula, and that is the empirical formula. So here is C6H6 and C2H2. Thinking in sort of broad terms about the number of carbons and hydrogens, what would you say is the same between these two compounds? The ratio. What is the ratio?
1 to 1.
It's 1 to 1. Here we have 1 carbon for every hydrogen. Here we have 1 carbon for every hydrogen. So what is the empirical formula of these two compounds? CH. C1H1, the CH. Both of these compounds have the same empirical formula. Do they have the same molecular formula? No. Are they the same compound? No. They're definitely not. This is benzene. This is not benzene. Okay? These are very different things. Okay? The molecular formula tells you exactly what you have. The empirical formula does not tell you anything all that useful in terms of molecular or covalent compound. What is the empirical formula of H2O2? HO. What is the empirical formula of H2O? H2O. You can't simplify it. So the molecular formula and the empirical formula of water is H2O. Are these two things different compounds? Yes. They have different molecular formulas, so they are different compounds. Okay. Here we have 3 different compounds that are very different from each other: cyclopentane, cyclohexane, ethylene. Ethylene is actually what makes your fruit ripen. They have different molecular formulas. They're different compounds, but they have the same the same empirical formula. Hydrogen sulfide, H2S, like water, the molecular formula and the empirical formula are the same because it cannot be simplified. Calcium chloride is ionic. By default, automatically, the formula that you write is the empirical formula. There is no molecular formula for an ionic compound. We can calculate these things, and this is actually why empirical formulas exist. On their own, they're not all that useful. But back in the old days, when they were trying to figure out what was in a compound, and this wasn't CSI or NCIS days, where they put a sample in a centrifuge and it tells them what's in it. They had to figure out what was in their molecule. Okay? And their instrument can't tell them how many carbon atoms, how many hydrogen atoms, how many oxygen atoms are in a single molecule. What their instruments could tell them was, in the sample that you gave me, what is the ratio between carbon, hydrogen, and oxygen? And so what it essentially is telling them is the empirical formula. The scientists then had to do other experiments to figure out what the molecular formula was. So we're going to come back to our chalcopyrite. This was our pie chart there. We're going to figure out the empirical formula of chalcopyrite based on the data that we were given. This was our percent composition. So every sample of chalcopyrite that you have will have the same percents. We're going to use those percents in our calculation. The first step in this calculation is to assume you have 100 grams. That's going to make our math easy. Because if we look back, percents, these add up to 100, right? And so if we assume that we have 100 grams, and it's 34.9% sulfur, how many grams of sulfur do we have? 34.9. So it makes the math easier if we just assume 100 grams. So we're going to assume we have 100 grams of chalcopyrite. We automatically know how many grams of sulfur, copper, and iron that we have. We then have to convert each one from grams to moles. Okay? So let's do that. The sulfur. I have 34.9 grams. How am I going to convert that to moles?
Divided by the atomic mass.
I'm just going to divide it by the molar mass. Yeah, sulfur is 32. 32 grams of sulfur equals 1 mole of sulfur. When you do that, what do you get? 34.9 divided by 32. 1.09 moles of sulfur. Now we have to do copper. We have 34.6 grams of copper. Copper is 63.55. 34.6 divided by 63.55 is 0.54 copper. Then we do the same thing for iron. We have 30.5. What is that? 0.546 moles of iron. We've calculated the number of moles of each one that we have. Let's see what the next step is. We have to take these numbers and change them into something we can use as subscripts. And our subscripts have to be whole numbers. They cannot be partial numbers. And so in order to do that, what we're going to do is we're going to look at our three numbers. We're going to pick out the smallest one, and we're going to divide all of them by that number. So of these three numbers, what's the smallest one? 0.544. So I'm going to go through it, and I'm going to divide all of them by 0.544. So automatically this one becomes 1. You divide it by itself. So that one is always 1. The smallest one becomes 1. What is 1.09 divided by 0.54? 2.00. What is 0.546 divided by 0.544? 1.00. Okay. So now we have whole numbers. These become our subscripts. And so we have S2, Cu1, Fe1. You don't need the ones, so you can erase them. So the empirical formula for chalcopyrite is S2Cu F.
Does it matter which order?
No. So here, they put what the calculator actually gives you. So they took it out more decimal places. And here they said iron is 1.003. The tricky part for these problems is knowing when you can round and when you can't round. Okay? You look at that and you say that is 1. 1.003 is 1. This is off because it came from a measurement. And every measurement that you take has error in it, right? And so if your measurement has error in it, your number of moles has error in it. And so you make the assumption that that 0.003 was error. That is really, really close to 1. 1.999 is really, really close to 2. That is 2. Okay? And so we get one of these, 2 of those. And so they put their order in slightly different order. It doesn't matter. So these are the steps. To me, this is just complicated looking. Convert them all to moles, divide by the smallest number, and you'll get subscripts. Okay? I think this one will be more complicated when we get to the end, and we won't actually be able to run. And so you'll see what happens in that case. So this is covalent. This is just copper and sulfur, and we're given the percents of each of them. How many grams do we assume? 100. So how many grams of copper do we have? 66.5 grams of copper. Copper was 63.55. Copper.
Yeah.
So how many moles of copper do we have? 1.05. Then we have 33.5 grams of sulfur. Sulfur is 32.07.
1.04.
This one is going to round. So what's the smallest number? 1.04. We're going to divide them both by 1.04 equals 1. Is essentially, it's basically approximately 1. So we get 1 and 1. So what is the empirical formula? Cu.
You have 1.05.
Where? Yeah, 1.05. Yeah.
The smallest.
Does this round up? Yeah, because this says this was
1.0445, so you have to like go into the round twice to get that.
It's tiny. It doesn't matter. This must be the one that where all heck breaks loose. This is Shattuck.
You make up your names.
I didn't make up the slides.
Okay.
If I made up the names, they wouldn't. There'd be something at least attempting to be funny, not Shattokite and Cobalite. 48.43 grams of copper. Copper was 63.55. What is the moles? 0.76. We go to silicon. We got 17.12. Silicon is 28.09.
If we leave off our units on the test, are we gonna be marked on?
Leave up units only for the answer. 609. Now we go to oxygen. 34.14 grams. Oxygen is 16. This is a spot that a lot of people get messed up. Before, we were saying the molar mass of oxygen was what?
16 is double that.
we said it was double that. That was because we were dealing with O2. Okay? O2, there are 2 oxygens. So the molar mass of O2 is 32. But here, the oxygen is not in O2 form. It is in a bigger molecule. So it's oxygen in a molecule, so it is just O, not O2. And so our mass is going to be 16. What does this come out to be? 2.13?
4.
1.4.
2.134.
Then we have hydrogen. 0.31 grams of hydrogen. 1.01 grams equals what?
0.307.
0.307. What is the next step?
Choose this one.
Divide them all by the smallest one. What is the smallest one? 0.307. So this one is obviously 1. That one, by looking at it, is approximately 2. That's very, very close to 2. What is this one? 2.48. Where does this one come out to? 6.95. Okay. So this one is exactly 1. That one was very, very, very close to 2, and so we said that one's supposed to be 2. What do you think that one's supposed to be? That one's 7. Okay? That cannot be rounded. That is clearly not 2, clearly not 3. What nice number is that closest to? 2.5, right? So we're going to call that 2.5. We're going to call that 7. But we can't have 2.5. We can't put 2.5 as a subscript in a compound. So what we're going to do is we have to take this number and multiply it by another number to get a whole number. I mean, we want to keep it as small as possible. And so just do trial and error. There you go. Trial and error or process of elimination. Same thing, not the same phrase. We're going to multiply it by 2. We multiply 2.5 by 2, what do we get?
5.
We get 5. But if we multiply copper by 2, we have to multiply everything else by 2. And so this 2 becomes 4, 7 becomes 14, and 1 becomes 2. So our formula, in the end, is Cu5.
Because you have to equal it out. You can't just. You can't do.
We got here,
Okay.
we had 2.5. We had to multiply it by something to get to a whole number. So we multiply it by 2 to get to 5. If we multiply that one by 2, we have to multiply them all by 2.
Because if you don't, it's all the equation off balance.
Correct. This is telling us the ratio. It's 2.5 to 2 to 7 to 2. But we can't have a point something. So to keep the ratio the same, you have to multiply everything by 2. So we get Cu5, Si4, O14, H2. H2. And then you pray that's what the slide says. Cu5, Si4, O14, H2. Good job.
And we pray that you get grades.
So this is those two compounds. This is benzene. Benzene is very reactive. It's a carcinogen. There's a lot of it in gasoline. This is acetylene. What's acetylene used for?
Neurotransmitter. Or no, that's acetylcholine.
It's acetylene.
Settling. For
What's
gas.
gas?
When you're doing cutting
Doing
steel.
Cutting steel, which is, how do you cut steel with fire? Welding. Acetylene torch. Have you ever heard that before?
I think so.
When you see people welding with a giant flame coming out of their hand, it's called they're burning acetylene. Okay. So that is acetylene. If you were comparing the mass of that to that, just in terms of a ratio, how many times heavier do you think that is than that? 3 times, right? Looking at it from that perspective, that is easy to see. Because that formula is 3 times larger than that formula, its mass is going to be 3 times larger, right? So now, next step is to take this empirical formula and calculate a molecular formula. And we're just going to use this principle, okay? That if a formula is 3 times larger, its mass is going to be 3 times larger. So if you don't know what the formula is, but you calculate the mass is 4 times larger, how much larger is the formula? 4 times. And so what these molecular formula problems are going to look like is they're going to make you calculate an empirical formula for which you can calculate the mass of the empirical formula, and then they will give you the molar mass of the molecular formula. And you have to figure out how many times bigger is the molecular formula than the empirical formula. If it's twice as big, you just multiply every subscript in here by 2. Okay? So let's do that after the break. We'll start at 7:30. I'll pass back the exams, but remember you have to turn them in. If you don't turn the exam in, you get a 0 on the quiz.
It's not even one. It's also, girl, this is dropping out my car. Ooh,
I'm telling you.
you like to listen. I'm gonna go out there and watch this video. You know what I'm gonna stay until he's completed that. Take all of his homework and all of my next class. I'm not going to all of my homework through the big code. You understand? I don't care if he comes. I don't care if he doesn't. But my homework is every day. So I'm not going to submit it to each other. I'm not going to submit it to each
Yeah.
other. You got any homework? I'll probably lucky. That's cool. That's you. That's today. Because at 10. We gotta get
Yeah,
this.
round.
It goes at 10 and then
Yeah, it should be like round.
oh, they might not have it up there.
Round.
Good. Okay. Did you? Like, you probably better than me.
Just a couple questions.
No, we got Sam not for that. No, we didn't. I know.
Oh, wait, that one? It's correct.
Okay.
I marked it wrong and marked it correct.
Yeah.
So same thing with that one.
Okay.
No.
Now, 15P,
I'm like, yeah, I forgot
we're
to.
talking about what left and down.
Smallest atomic radius would be top right.
That was L.
What?
I know something.
Oh, so I'm sorry. Smallest atomic radius is bigger bottom. Biggest is bottom left. Smallest top.
Smallest would have been.
Stop.
Small top right.
Okay. Okay, I just,
I want to add what?
I see where I went.
Look, I'm trying to get it. What you got to say? Oh, I guess I'm sorry. This should be nice. Should be nice.
Mark it wrong and mark it right.
Oh. Maybe I'll text you.
You about to text me? Okay, text me. Did you text me?
No,
I don't see it. I see a message, I don't know if it's you.
that's not me.
Okay, then text me quickly.
I'm trying to find your number.
Just
do it now.
Hurry,
There you go.
This is big
You
one. That
can't
was
tell
the-
me you're
waiting.
texting me
I
and
didn't
then
say
you
it
can't
out
text
loud.
me.
You going home?
Right. So you had to get,
You
put
going
that
home?
number into sig things, which is
My head is
0.001.
down.
Now,
Not two decimal places, sig.
I am like, no.
but even because it was a point, it's such a smaller number.
Are you going
That
home?
made those two count. That's-
I didn't
No,
think so.
no. Leading zeros are never
I have to think about how.
Even
my
leading
head
zeros
is
are
gonna
never
be.
ever ever.
Okay.
Oh my
Trailing
God.
zeros are
Listen, we're
significant
not
if
gonna
it's a
have
decimal.
time even after this close.
I think that's where I messed up.
I'm going to my apartment.
Oh my goodness.
Question?
Yeah.
Oh, that's marked wrong and then marked right.
Okay.
That's enough.
Just wanna make sure.
Apparently,
It's cool, it's okay.
on my answer sheet on the computer, I had the right answer, but then when I made the key, I somehow wrote down the completely wrong letter.
How you get one?
Should have been two.
Let me see. Let me see.
Hold on.
What you think? He said A.
He said C.
He says A.
Calcium?
No, 10.
Oh. I said B. He says A.
Yeah, he says
Yeah, right one.
That's what I'm saying. But you already got it messed up. So, carry on.
What you mean I got it messed up? I want extra.
Okay, well, that's these going to place you have to say the name.
No, it's not. There'll be a couple points.
No, you won't, because you won't.
It don't matter. I couldn't get that.
You're supposed to have 22.
But he didn't give it. It don't matter. He
That's,
gave me
that's,
25.
no, he won't. How can we do 25 or 25? You're supposed to have 22. You better just shut up.
What? He can't go.
Yes, he can.
No, he can't. It's not a problem. You can't change.
Yes, he can. No, we are going to No.
Not really, just because he, like, when he was looking at the sheet that he wrote on the paper, it was wrong, but so he copied that one, but the sheet on the computer, he just went through and was like, marked it, like, what I've written down. But if you answer it wrong, that's wrong.
No, it's right.
Oh. Yeah, so you had a front class, that's right.
You better. Okay, you say something. Because all of it,
You see where it says like a little,
it's in
Oh, okay.
I just said,
sorry, I probably.
you know, I'm just mad at the situation.
Why?
And
That's probably what it is.
what's it?
Trying to change.
Don't forget, you gotta turn this back in. Everybody wanna turn it in now before they forget?
Can I have it? I want to study for the final.
So for studying for the final, you're gonna use the cumulative homework that you just turned in. They're very, very, very similar.
I was gonna say that reminded me of the did you bring it?
Smallest ionization energy.
It's two, that's not
Smallest.
so the bigger is I got this too. I just told you the way it's
Actually, no, that way, you know, like, I get it on the sides of the bottom.
Wendy, you can't get the whole point. Stop. Huh?
It's not that.
That was on that.
Yeah, he's missing it.
I don't care.
Grant.
I don't care.
Oh, we have to ask, oh, may I?
You can have them, but just remember, don't
Consider that 98.
Yeah, I'll give it
turn
back
them
to
in before you
you.
leave.
You got mine?
We're gonna get a 0 on the quiz, you said?
That's why I need to go ahead and do it. You got dogs in the back.
So the ones that marked okay, is that right?
Mark, okay.
Give me your wallet. Give me your card. My card is in the car. So I can get some grandma cookies. So,
Mine's probably on the bottom, but it's there.
Me?
no.
Anybody else?
What trying to sound back?
Okay. So we're going to pick up on our molecular formulas. And just like with the molecular shape problems, where it's a Lewis dot structure formula taken another step, molecular formula equation is an empirical formula question taken one step further. Okay? And so the type of problem that you would see here is a written problem. Part A, calculate the empirical formula, and then part B, take it an extra step to find the molecular formula. And so in order to find the molecular formula, you are going to calculate the empirical formula and calculate the mass of the empirical formula, and then you will be given the molar mass of the molecular formula. So in ye olden days, their instrument would tell them the ratio between the different elements, which is the empirical formula, and then they would have another experiment to figure out the molar mass of the molecular formula, and then they can do what we're about to do to find what the actual molecular formula is. And so, two steps. Find the empirical formula, divide the experimental molar mass, which is the molecular molar mass, by the empirical molar mass, which is exactly what we just talked about. And so if the molecular formula has a mass that's twice as big as the empirical molar mass, then your empirical formula is twice as big. And so you'll take your empirical formula that you calculated, and you'll just multiply all the subscripts by 2. So here we have a formula, CH2. And there's no name on it. I can make one up though, so you don't want me to. So we have CH2. Molar mass is given to us. The molar mass means of the molecular formula. It's 42.12. What is the first step we have to do? There are 2 steps to find the molecular formula. What's the first one? Find the empirical formula. So it's a very big, long step. So we've got carbon. How are we going to do this? There's no percents given.
It's
Oh, thank you. Thank you. Yes. I was going to go in a giant big circle to end right back up where we started. So the empirical formula is CH2. How are we going to find the molecular formula from that?
Determine the mass of that and divide by the molar mass given.
Correct. I think there's a little bit about syntax about what he says, but we'll get there when we get there. So what is the mass of CH2? Carbon is 12, hydrogen is 1. So what's total here? 14. We'll just call it 14. Okay. So the empirical formula is 14. The molar mass is 42. So this is the experimental, the molecular over the empirical. And so it's 42.12 divided by 14. The bigger one ends up on top. The goal here is to make our formula bigger. If we put the small one on top, that's not going to happen. So if I divide 42.12 divided by 14, what do I get? 3.01. What number do you think that actually is? 3. 3.01 is 3. And so if my empirical formula is CH2, and my molecular formula has a mass that's 3 times larger, what is my molecular formula? C3H6. 1 times 3 is 3, 2 times 3 is 6. My molecular formula is C3H6. I really should make a problem that comes out with the answer C3PO. Now we've got another one, potassium persulfate. This one we're not given the empirical formula, so we will have to actually calculate it. So we've got 28.93% potassium. So we have 28.93 grams potassium. Potassium is 39.1. 39.10. How many moles? 0.73. Sulfur, got 23.72 divided by 32. Equals what? .74. And then oxygen, 47.35. 16 grams equals what? 2.96. Now what? Divide by the smallest one. This is a step that a lot of people forget, okay? You're going to remember today. When you go to do it a week from now, you may forget. And a lot of people will be tempted to round that to 1, round that to 1, round that to 3, and stop. That's not what you're supposed to do. Divide by the smallest one, which is 0.73. So that's 1. That's essentially 1. What does that come out to? 3.97, which is what? 4. So our empirical formula is K1 S1 O4. So that is our empirical formula. How are we going to find the molecular formula?
Add the masses of that formula.
Add the masses of this. When you do that, what do you get?
135.17.
135.17? Okay. So you get 135.17. We're given the molecular formula mass of 270. What am I going to do with those two masses? Divide big one, 270. Oh, divided by 135.17, and that is essentially 2. What do I do with that? Now I got the 2.
Multiply the formula by that.
Take the 2, multiply it by that. So essentially what I get is K1 S1 O4 times 2, which is K2 S2 O8. Or K2 S2 O8.
Can you explain again, what's the experimental mass? Or what is that?
So that is the mass of the molecular. molar mass of the molecular formula. And so that equation I have to call it experimental, because in the real world, that would be something that someone measured.
Okay.
And so you do two experiments, one to find the empirical formula, one to find the molar mass of the molecular formula, and then do this to figure out what the actual molecular formula is. Does this make sense? Find the empirical, find the ratio between the masses, whatever that number is, multiply it by the empirical to get the molecular. You will see it multiple times on exams coming up. Okay. We're going to move on from this math stuff a bit, and we're going to get into reactions. Is it a cheer of joy?
Nope.
So we're going to write chemical equations. And we've already done that somewhat. We said that you have reactants on the left, and then you have the yields arrow, and then it gives you products. If we write an equation, it has to be balanced. And when we say an equation is balanced, that means that however many of one element we have on the left, we have the same number of atoms of that element on the right. We are going to rearrange atoms in this class. We are not going to destroy atoms. We're not going to create atoms. We're just going to rearrange them. So what you start with is what you're going to end with. And so when we first write a chemical equation, it's not going to be balanced. You write the equation, and then you balance it. Okay? This is the reaction of iron 3 oxide with aluminum. Okay? So this is the reaction. Aluminum solid plus iron 3 oxide solid gives us aluminum oxide solid in a liquid iron. So this tells us that these two things yield these two things. These are our reactants. These are our products. If we look at the equation that we're given, we just look at how many of each element are on the left and how many are on the right, we see that on the left there's one aluminum, on the right there's two aluminums. 3 oxygens, 3 oxygens, 2 irons, 1 iron. Would you call that balanced? No, that is not balanced. What could you change in order to make it balanced? If you can gain an aluminum, you can't necessarily lose an iron. I'm assuming you'd want to take one away from here. If you take away that iron, then it's not iron 3 oxide anymore. So you can never take anything away. You can add an iron to the right. If we started with 2 irons over here, that means we're going to end with 2 over here. We can never change the formula themselves. Once we figure them out, based on their charges, they are what they are. We add what he called coefficients. You can add numbers in front of them to say how many of these, and how many of these, and how many of these, and how many of these that we have. So we need an extra aluminum on the left. So we can just say we have 2 aluminums here. And we need an extra iron on the right. So we can just say we have 2 irons. If we do that, it's now balanced. And in the end, that's what we end up with. We just added a 2 there and a 2 there, and we're now balanced. Balancing is another one of those things that in principle is not that difficult, but it's like a puzzle. The more times you do it, the quicker you're going to be the next time you do it. This one is really easy. They're not all that easy. The one on the final exam is not easy, okay? Every year, people come up to me and tell me this thing can't be balanced. They just haven't taken it far enough, okay? Keep plugging away at it when you get to it, okay? You'll see what I mean by a not easy one when we get to it today. So here's another reaction. This is methane burning with oxygen to give us carbon dioxide and water. When you look at an equation, you got to figure out whether it is balanced, because you can't use an equation unless it's balanced. So you look at that, and you say, how many carbons are on the left? There's one carbon, and one carbon on the right. How many hydrogens are on the left? There's 4 here, and 2 over there. That's not balanced. 2 oxygens on the left, and 3 oxygens on the right. 2 there, and 1 there. So we have to balance this. Okay? Always balance with pencil, not pen. Or otherwise it gets really, really ugly. So we have CH4 plus O2 yields CO2 plus H2O. Just some tricks that you'll learn. Always start with the things that are not hydrogen or oxygen. Okay? So in this case, that's carbon. But carbon's already balanced, so we don't have to touch that. I always do hydrogen last, because it's usually the most different. So let's do oxygen next. Oxygen is 2 on the left, 3 on the right. Something that's going to save you some time is to notice that all of these oxygens come in pairs. Right? I have 1 pair of oxygen. If I put a 2 there, I'm going to have 4. If I put 3, I'm going to have 6. And so there is no way that I can get an odd number of oxygens on the left. There's no way. I have an odd number of oxygens on the right. These oxygens come in pairs. Those come in singles. So if I have an odd number as the coefficient here, I'm going to have an odd number of oxygens on the right, which means my coefficient on that oxygen has to be an even number. And so where I would start is I would just put a 2 there. I'd put a 2 and see where that led me. How many oxygens do I now have on the right?
4.
I now have 4. There's 2 here and 2 there. Total of 4. I only have 2 on the left. I only started with 2, so what can I do? I can add a 2 there. So I now have 4 oxygens and 4 oxygens. So now we move on to the hydrogen. We have 4 on the left. How many do we have on the right? 4. Now we have 4. When we fix the oxygens, we also fix the hydrogens. So that equation is balanced.
So you said you can't use like fractions, like if you were doing 3, 2.
That coefficients have to be whole numbers, which is why it can sometimes we really multiply up. And there's a tough one coming up. So that is our balanced equation. These are just some general steps to follow. Potassium chlorate yields potassium chloride and oxygen. KClO3 yields HCl plus O2. What type of a reaction is that? Decomposition. We have one product, it breaks apart, it decomposes, it's decomposition. Are my potassiums balanced?
Yes.
Yes. Are my chlorines balanced? Yes. Are my oxygens balanced? No. What do you see? How many oxygens?
3.
And 2. These oxygens come in pairs. This is an odd number. What's the first thing you would do? I would stick a 2 there, get an even number of oxygens and see where that leads me. So, I put a 2 there. Now I change how many potassium and chlorines I have. Are my potassiums balanced?
No,
No. How can I fix that?
2 on the other side.
I can put a 2 there. I now have 2 potassiums. When I did that, I also fixed the chlorines. How many oxygens do I have?
6.
I have 6. 2 times 3 is 6. What can I do over here? Put a 3 there.
It's kind of like when you do the charges across.
But you can see, when we added the 2 here to fix the potassiums, luckily we fixed the chlorines at the same time. But a lot of times, when you fix one, you're going to break another one. And then when you refix chlorine, you're going to re-break potassium. And you keep going back and forth until you figure out where you're supposed to be. Oop, the other one. Hexane, C6H14, C6H14 plus oxygen gas yields CO2 plus water. Carbons balanced?
No.
Yeah. What should I do?
Add a 6 plus
I got 6 carbons here, 1 there, so I'm going to put a 6 there. Carbons are now balanced. I'll save hydrogens for last, so I move on to oxygen. How many oxygens do I have over here? 2. How many over here?
3.
Careful. There's 12 there, plus 1 is 13. That's an odd number. First thing I would do is pick a 2 there and see if that solved my problem. I now have 12 plus 2 is 14. How many do I have over here?
2, so you have to add 7.
I have 2. I can add a 7 there. And I'll have 14 on the left. Are my hydrogen balanced? I have 14 here. I don't have 14 over there. What can I do to this to get 14 hydrogens?
Make it times 5.
How many waters do I need to get 14 hydrogens?
7.
I need 7. So I'm going to erase my 2. I'm going to put in a 7. But that's a problem. 7's odd. I now have an odd number of oxygens. So what do you think I can do? Well, let's go with it, okay? If I have 7 of these, I now messed up my oxygens. How many oxygens do I have over here? I have 12 plus 7. How many? 19. So what do you think I can do? I can't have an odd number here. Adding carbon's not going to help me. Take a look over here. The oxygens over here come in pairs. I can put whatever number I want here, and that's not going to affect the number of hydrogens or carbons.
So put it even.
So any number of oxygens that I get over here, I can deal with. And so as long as it's an even number. So I'm going to take that 7, and I'm going to multiply it by 2. I'm going to double it. I'm going to put 14. Now I have 14 times 2 is how many? 28. Can I get 28 hydrogens over here?
No, you can add a 2.
I can, because they come in groups of 14. So I have 2 of those, and I'll have 28 and 28. But I now have 12 carbons. So now I have to put 12 over there. But now my oxygens are all out of whack. I have 14 oxygens. Here I have 24 plus 14 is 38.
Divided by
But that's an even number. And I can put any number here that I want. Half of 38 is 19. So now everything should be balanced. 12 carbons, 28 hydrogens, 28 hydrogens, 38 oxygens, is 24 plus 14 is 38. That's the type of problem you just got to keep plugging it. You'll get there eventually. It just keeps getting bigger and bigger and bigger. Make sense? See what I mean by it's not hard.
Just like a puzzle.
It's a puzzle. And when you change one part of the puzzle, you change another part of the puzzle. You want to do the last example? You want to move on? Move on. Want to do it? You want to do it?
No, yeah.
Does somebody want to do it up here?
Nope.
Is that what's on this slide?
Is the answer already there? Does that mean you want to do it? This is probably going to be much easier than this one. We've got zinc plus hydrochloric acid yields zinc chloride plus hydrogen gas. My zinc balanced? Yes. Chlorine balanced?
No.
No. Got 1, I got 2. Stick a 2 here, now my chlorines are balanced, now my hydrogens are balanced.
The one on the final exam, is it gonna be like, are we gonna have to use triple digits?
Like over 100? No, I don't think it's like that. It's more like, I think the numbers are bigger than this one, but they're not 100.
Okay, good.
Wendy, I'll be right.
It's just, like, I'm trying to figure out how to, I've learned a different way where you have to write everything out, like, you write it in a row.
I've seen students do that. That is not how I do it. If that works for you, you're certainly welcome to do that. But if you ask me a question, I'm going to be learning as I go. And do this next.
How do you determine, all this time I thought you look at the periodic table to see how many valence electrons to balance the chlorine and the zinc, so it's not that.
So the number of valence electrons will dictate the subscripts.
Okay, so we start with the left balancing the right?
Where, I mean, you can count the right before you count the left. It's just naturally we start on the left and move right.
Okay, but that depends on the valence.
The valence electrons will determine the subscripts. That's why this is HCl and not HCl2.
Okay.
So you figure out the proper subscripts, and then you balance everything using coefficients. You figure out the subscripts, and then once you get the right subscripts, you can't change them.
Someone else says the fractional coefficients are acceptable, so that means it can't be the 9.5 as you go. So that's not correct.
Let me see, guys. Yeah. So what she's saying is, this says fractional coefficients are not acceptable. And so when they were doing this, they actually did balance, got it balanced by putting half of a number here. And then said, okay, it's now balanced, but I have 9.5, which I have to multiply by 2 to get to a whole number. And so they multiplied everything by 2 to get to where we got. This is where our video picked up. So we've got the 4. The decomposition is one reactant that breaks apart to multiple products. Synthesis or combination reaction is multiple reactants that come together to form one product. And then there was a single and double displacement, which were a little more complicated. Actually, this is a really good place. Really good place to stop, so we'll stop here. So we'll pick up here after the lab on Thursday. And so now we'll go over some of the homework before the quiz. Yes.
Right, so the homework for tonight is what we only went over.
how do you know if something is a synthesis reaction? It starts with at least 2, and then you end up with 1. Okay? Then we had single displacement. In the single displacement, unfortunately, there's only one. It's all or nothing. But if you do that, can you see the board?
I think so.
Yeah, yeah.
Actually.
I get, you could open, oh, well, those are open. It's not very light.
Good luck seeing the board in the video.
That's what I was just looking at. It looks fine.
Did it?
Yeah.
Okay, we'll see. So in single displacement, we had a compound, and then we had an element. In the single displacement, the element here, it's going to be a metal, and it's going to kick out the metal that's in the compound. That'll give us a new compound, and then the metal that was in the compound is now off by itself. That is a single displacement reaction. Then we had double displacement. In the double displacement reaction, we have 2 compounds. All right? And all this is switching of partners. The metal from this compound ends up with the non-metal from that compound. The metal here, E, ends up with the non-metal, D, over here. And so it's just switching partners and seeing what you get. So in the video, we talked about this activity series. How do you use the activity series?
The metals up on the top are stronger and they pick the ones that are underneath them out.
Exactly. The higher you are up on the table, the stronger you are. And so if you are stronger than the metal that's currently in the compound, you're going to kick that one out. But if you are weaker than the metal that's already in the compound, nothing's going to happen. Because you're going to try to push it out, but they're just going to push back and nothing's going to happen. So this slide wants us to write an equation for calcium reaction with water. So in this reaction, we need to think of water not as H2O, but as hydrogen hydroxide. So we're looking at, can calcium kick out hydrogen? Based on that, is there going to be a reaction? Calcium is there. Hydrogen is down here. So calcium is stronger. So this calcium is going to kick out that hydrogen. We're going to get calcium hydroxide and hydrogen gas. Is that balanced?
No.
No. Here we have 2 hydroxides. Here we have 1. If I put a 1 there, that also balances. Get 2 of these, single hydrogen gives that one H2. So that was how we predicted single displacement reactions. We used the activity series. Remember that. Yes?
Are we going to have this on our cheat sheet?
This is on your cheat sheet. So the activity series is on the cheat sheet, and the solubility table is also on your cheat sheet. And so what you need to remember is I use the activity series for single displacement, and I use the solubility table for double displacement. I've seen plenty of people trying to figure out whether a single displacement reaction is going to happen looking at the solubility table. And I've seen plenty of people trying to figure out whether a double displacement reaction is going to happen looking at the activity series. That's not going to help you. In the double displacement reaction, we said all we're doing is switching partners. Switching partners is easy, right? Once you've done it once and you see how it works, you can always do it. But that's not the end to a double displacement reaction. Because the answer to a question that says write the reaction from these products could be no reaction. Just like in the single displacement, we have to figure out which one is higher. The one that's already in the compound is higher, nothing is going to happen. In a double displacement, we're looking for solubility. So this is a solubility table. The one in the cheat sheet doesn't look exactly like this, but it tells you the same thing. So it tells you which compounds are soluble and which ones are insoluble. So the way to reread this is anything that has sodium, potassium, or ammonium is soluble. It doesn't matter what the negative ion is. If you have a nitrate or acetate, it is soluble. It doesn't matter what the positive ion is. Here, anything with chloride, bromide, or iodide is soluble unless the metal is silver, mercury, or lead. Does this table make sense to you, how to read it? And so in a double displacement reaction, what you're looking for is a product that is insoluble. When you switch partners, you're going to make two products. If they are both soluble, nothing's going to happen. Because if it's soluble and it's dissolved in water, it's going to be broken up into ions. So if you put your two reactants in the water, it breaks up into four different ions, two positives, two negatives. But if your products are soluble also, they're going to immediately dissolve. And so on the one side you have 4 ions dissolved in water. On the other side you have 4 ions dissolved in water. They didn't actually do anything. But if one of your products is insoluble, then you're going to get a solid that forms and it's going to sink to the bottom of your beaker. So we have this reaction, okay? We're mixing lead nitrate with potassium iodide. If we switch partners, what two compounds do we get? We get lead iodide and potassium nitrate. Does everybody see that? If we switch partners, we get lead iodide and potassium nitrate. So let's go back to our table. We had lead iodide. Is lead iodide soluble or insoluble? It's insoluble. It is iodide, but it's lead. And this says lead iodide is an exception. It is insoluble. What about potassium nitrate? Soluble. Anything with potassium is soluble, and anything with nitrate is soluble. So it's very, very soluble. So we have one insoluble product, and that's this yellow solid that's forming here. So you're pouring two clear liquids together. When they mix, the two ions combine together to make this yellow solid. Did you have a question?
Yeah, so when we have a question like this on a test, do we just say that it participates or precipitates?
You would have to write out the products.
And you wouldn't have to you wouldn't have to say if it's insoluble or soluble or not?
You will. And so we said we made potassium nitrate and lead iodide. You notice the reactants there have AQ on them for aqueous. That means they're dissolved in water. You have to put state symbols on your products also. And so when you look at that solubility table and you see that potassium nitrate is soluble, you put aqueous. When you see that lead iodide is insoluble, you put solid. So there's lead iodide solid, potassium nitrate aqueous, and it does not matter which one you write first. here is another example. I think this is the first slide that we didn't cover in the video. Is that correct? Anybody know? Yeah. Okay. So we're mixing two solutions. Cadmium 2 nitrate, which is this, and sodium sulfide, which is this. It says Jennifer obtains an orange precipitate that is a pigment known as cadmium orange. Identify the precipitate and write a balanced chemical equation for the reaction. So, we have the reactants up there. Because we're going to have to balance them in the end, I'm going to rewrite them up here. Got cadmium nitrate aqueous plus sodium sulfide. If I switch partners, what two compounds am I going to get? Cadmium sulfide
Sodium nitrate.
plus sodium nitrate.
Do you have a black marker that we can use?
I do, but it wasn't working as well as the red one. Let me see if mine will work better. So we have cadmium from this one, sulfide from this one, they give cadmium sulfide, sodium from this one, nitrate from this one, to give sodium nitrate. And so now that we've got those written, let's go back to here. Is cadmium sulfide soluble or insoluble?
Bring that two with each other.
Which two?
There's two nitrates.
We'll balance it at the end.
Oh.
So you write the subscript based on the rules that we learned. So cadmium is plus 2 charge, sulfide is minus 2 charge. So it's just CDS. And then we'll balance everything at the end. Cadmium sulfide, soluble or insoluble? How do you know it's insoluble?
Because sulfides are insoluble.
Right. Soluble, sulfides are insoluble unless they're with ammonium or group 1. Is cadmium ammonium or group 1? No. And so cadmium sulfide is insoluble, so I'm going to put soluble. The other one we have is sodium nitrate. Soluble or insoluble? Soluble. So I'm going to put aqueous. So the first part of our question said to identify the precipitate. What is the precipitate? Cadmium sulfide. All right. So it says it's cadmium orange. Cadmium orange is just a common name for cadmium sulfide. And then we have to write the balanced chemical equation. We've written the equation, but we just have to balance it. What is out of balance? Sodium and nitrate. I have 2 sodiums and 2 nitrates here. I have 1 of each here, so this one's easy. I can just put a 2 there. And I balance both at the same time. So here's another one. Barium chloride and sodium chromate. You don't even need to know what chromate is to do this reaction. If you switch partners, what are you going to get?
Sodium chloride and barium chromate.
Or you get sodium chloride, NaCl, and barium chromate. Is NaCl soluble? Do you even have to look at the table? It is soluble.
It's just salt.
It's salt. And so that is aqueous. A little test taking exercise. Do you need to look at the table to figure out whether barium chromate is soluble?
No.
Why not?
Yes. No, I'm not. Oh, I was thinking of the periodic table.
Right,
where it
it's
is,
so-
that's why.
You're on the right track. So we already said sodium chloride is soluble. But how do we know that barium chromate is not also soluble and it's a non-reaction?
So given that.
Given that a precipitate forms in the reaction. The question is telling us that there's a precipitate. But we know for sure that sodium chloride is not our precipitate. So this one must be.
So it doesn't go by where they are in the periodic table?
No. You need to look at that. If you can't figure it out based on the question, you need to look at the solubility table. You cannot look at the periodic table and figure this out. So we need to balance it. I've got one barium on each side. I've got 2 sodiums on the left, 1 on the right. I'll put a 2 here. That fixed the chlorines at the same time. I think that should be it. Is that it? Is everybody getting this balancing thing down? How many want lights on? How many want lights off? Oh, wow.
If you write more on the right side of the board, because the problem is that.
Yes,
This
What
side
if
actually.
from the reactions are long.
What if I close the blinds, because the light is what's blocking it?
Yeah.
You can try it.
Yeah, do it your own way.
Or you could just grab it over.
That doesn't do anything.
No.
Now they're gonna say that they can't see.
Better or worse?
Turn the light, try turning the light on now.
leave the lights on, call it a day.
Lights on?
Yeah.
Okay.
Thank you.
I think you can see that.
I can see,
You can see that. Just candy. A whole lot cheaper than the theater. An acid-base reaction is a double replacement or double displacement reaction. The slides say double displacement. I like to say double replacement. They're interchangeable. Okay, it doesn't matter which one I say, which one the slides say. It's the same thing. An acid-base neutralization, where you mix an acid and a base, is a double replacement reaction. It's a specific type of a double replacement reaction that we're going to talk about a lot more in a different later lecture. So we're not going to really touch on it too much here, but when you mix an acid and a base, you get 2 products because you switch partners. One of them is always water. If you acid-base reaction is going to make water and a compound. That compound is going to be a salt. Acid-base reaction gives salt and water. But we'll come back to that. That's not that important at this point. We've got combustion reactions. A combustion reaction is kind of its own type of reaction. It doesn't really fit in to any of them. Because basically you take one thing, you add oxygen, and then you get a whole bunch of things. And so you end up generally with more things than you started with. So that would make it seem like it's a decomposition, but you have 2 reactants. And so that seems more like a synthesis reaction. A combustion reaction, burning things, is really its own thing. So here, this is methane, CH4, that's what's in our Bunsen burners, reacting with oxygen, O2. We get water and CO2. Two entirely different things. That's not synthesis, that's not decomposition, it's not single replacement, it is not double replacement. It is its own thing. But combustion reactions are very easy to spot because all they are is something plus oxygen. Burning is just a reaction with oxygen from the air. That's all burning is. It just happens very, very quickly. All right. So we need to classify these reactions. Which type of reaction is that? Decomposition. We got one reactant becoming multiple products. That's a decomposition. What is this one? Synthesis. Two products becoming one reactant. Sorry, backwards. Two reactants becoming one product. This one? Single. You have a compound and an element. Without even looking at what the reaction does, you have a compound and an element, and so it's going to be single displacement. What's this one? Double. What is this? Synthesis. We have one product. If you have one product, you made something new, that's synthesis. What is this? Double. We switched partners. We ended up with copper sulfide and sodium chloride. This one? Decomposition. We have one reactant, multiple products. What about this one? Single displacement. The calcium replaced the lead to give calcium chloride and lead. Now this one's tougher. You can't even see what the reaction is. Just looking at the picture, trying to get some clues about what's going on. What do you think this is? Why do you say it's double displacement?
Well, it has a precipitate.
There's precipitate, so that's number one, right? And so we're making a precipitate. With precipitation reactions were a type of double displacement reactions. Just like what we did here, we mixed two solutions. Here we have the clear solution in the flask, and we have the solution that's in this dropper. Those are two solutions that we're mixing together. And if you do that, we're going to get a precipitate. In this case, when you switched partners, they were both actually solids. And so we're getting a yellow precipitate solid and a purple precipitate. What do you think this is? Combustion. How do you know? Burning. What do you think this is? If you don't know what this is, acid base. Why do you say it's acid base? It's a pH meter. So we haven't talked about pH yet. We will, but you probably know pH has to do with acidity, right? And so this is a pH meter. This is an acid-base reaction. This is very hard to tell, but there is a solution down here in the beaker. Then there's a chunk of metal sitting in it, and it's giving off probably a very toxic gas. What do we got? I got a double and a single. Got another double. Got a no idea. The trick is to look at the reactants. What are our reactants? So we have a solution down here. Do you think that is an element or a compound? It's a compound. Okay. If it's in solution, it's probably a compound. Then we have a chunk of a metal. Do you think that is probably an element or a compound? Probably an element. So if we have an element reacting with a compound, that's single displacement. What about this one? So a drop, this is a test tube with a clear solution in it. A drop came in and it made this white stuff. Double displacement. With two solutions again that came together, swapped partners, and we end up with one solid. This one? Combustion's burning. Can't even tell what that is.
Looks like acid.
Which one?
KOH. Can you read what that says?
Well, OH, that's got some kind of
Silver nitrate. It's potassium hydroxide here. Silver nitrate there. And so if you're mixing potassium hydroxide and silver nitrate, what do you think it is? Double displacement. Those are two compounds.
So single displacement is a metal and what? When you mix a metal?
A metal and a compound. So here we have a beaker of a solution and a chunk of, let's say, strontium. What do you think that is? Single. We have strontium displacing something in the solution. This solution may just be water. Because remember before we had the reaction of calcium with water. And we displaced hydrogen to make H2. This is bubbles coming off. There's another way of looking at it. What type of reaction is that? How many reactants do we have? Two. How many products do we have? One. What is it? Synthesis. What's this one? Decomposition. We just have one reactant.
Synthesis, is it not mixing similar things together?
It doesn't matter what you're mixing. The synthesis has one product.
Yeah.
A synthesis reaction, it doesn't matter what is over here. As long as it is more than one thing, and you get one product,
Okay.
that is a synthesis. You're taking multiple things and just sticking them together. You're synthesizing something. And this is decomposition because you have one reactant. If you have one reactant, all it can do is fall apart. And so it's falling apart into this. This one. Single. We have a compound and an element. The blue kicks out a green to make blue-green. And the last one? Double. Just switching partners. What about this one? Synthesis. We have one product. Without even really looking over here, we have one product. So the only thing it can possibly be is synthesis. This is something that is going to drive you batty. Okay? This is another one of those things. It's not hard, but there are a lot of steps involved, and there's a lot of work involved. Okay? This is how we're currently writing a double displacement reaction. There are other ways that we can write it. Okay? And so if we, in these situations, our reactants are aqueous. They're happening in water. And so what we wrote here is called the molecular equation. A lot of times you'll have a problem that asks for the net ionic equation. And just like we had to draw the Lewis structure in order to get the molecular shape, you have to make molecular equation before you can get the net ionic equation. And what this is really working on is the premise that if something is aqueous, it is broken apart. If it's an ionic solid that's dissolved in water, it is broken apart into ions. And so we don't actually have cadmium nitrate in our liquid. We have cadmium ions and we have nitrate ions. We have sodium ions and we have sulfide ions. It is not sodium sulfide. And so you end up with a pool of 4 different ions that try every single possibility that's there, and if one of them makes something that's insoluble, it then sinks to the bottom. And so the net ionic reaction is going to take into account the fact that we're not dealing with actual compounds here. We're dealing with ions. So we go from the molecular equation to what we call the ionic equation, or the total ionic equation. So we're going to go molecular to total to net. So in this case, this is our molecular equation. We've got what did I do with the good one? That is a molecular equation. To get our total ionic equation, we go through, in anything that says aqueous, you break into ions. If it says solid, liquid, or gas, you leave it as it is. So this says aqueous. If I break that into ions, what do I get? Silver and nitrate ions. So I get silver ions. Make sure you put the charge. It is aqueous. I get nitrate ions that are aqueous. Then I get what from this? Sodium and chloride. This is a solid, so I do not break it up. I just copy it down here. And then what do I get here? Sodium.
Or I could put a 2 next to the boron.
There?
Yeah.
But then that's an S for solid.
No,
Oh,
right
the
beside
2
it
right
is a
next
2
to
instead of the
Oh,
boron.
I don't know why I pointed at the S, not the That is the total ionic equation. Obviously, there's a lot of things to write.
It's just broken down more.
It's just broken up, yeah. But there's a lot of things that you can forget there. There's a lot of charges, there's a lot of state symbols. And yes, if I catch it, I will mark it wrong if you leave one of them off.
The whole question is
Just that.
so like,
You get plenty of like
Partial
partial
credit.
credit.
Yeah, no, if you left that positive off, that would be almost insignificantly small. But if I caught it, I'll mark it.
What is it called when you cancel out the same ones on each side?
That's what we're about to do.
Okay.
So this is molecular equation. This is the total ionic equation, or the ionic equation. What she was asking about is the net ionic equation. The net ionic equation is just telling us the reaction that happens. Because, if you think about it, we have sodium ions and nitrite ions over here. We have sodium ions and nitrite ions over there. The sodium and the nitrate didn't actually do anything. They just sat there. And so they don't really belong in the reaction. And so the net ionic equation just tells us what happened. And to do this, all we do is we go through and we cross out anything that is on both sides. So is there a silver ion on both sides? No. Over here, it's in a compound, so that doesn't count. Is there a nitrate on both sides? Yes. So I'm going to cross the nitrates out. Is there a sodium on both sides? Yes. So I'll cross those out. Is there a chloride on both sides? No. The chloride is in a compound, so that doesn't count. Now, all I do is anything I did not cross out, I copy down here. And so I get silver ion plus chloride ion yields silver chloride.
So it's just the two ions that come together.
Exactly. It just tells you the two different ions that come together to give you a precipitate. So if you're comfortable enough with this, to look at that and say, well, my precipitate is silver chloride, so it must be silver plus chloride, that's fine as long as the question doesn't ask you to really write the total ionic equation out. Okay? If you're comfortable, you can jump from the first one to the third one. If you're not comfortable, I really, really suggest writing this out and then just crossing off the ones that are on both sides. You can't go wrong as long as you break the aqueous things up and don't break up anything that's not aqueous, and then just cross them out and copy down what's left.
You said the aqueous are not really compounds, they're just floating together.
Right. If they're aqueous, that means they're already dissolved. And so if they're already dissolved, the silver is over here, the nitrate's over there. It's not silver nitrate. It was silver nitrate before you put it into water, but now it's not.
What do we call this step, by the way, when you
Which-
cancel out?
The actually crossing them off,
Yeah, the last one.
the last of the net ionic equation. The ones that we cross out, we call spectator ions, because they just sit around and watch. They spectate. Is that a verb?
Yeah, yeah.
Is it?
Yeah.
Okay. Is it? You sure?
Yeah.
Okay.
It's an action.
Just like it's on
So there's a number of slides going through what we just did. And so when we get to the end, it's the net ionic equation. Silver plus chloride yields silver chloride. Does this make sense?
A little bit. That's just the one. Can I do another one?
Here's one. We've got barium sulfate.
This one's intestine.
Yes. And so it says you make barium sulfate by mixing barium chloride and sodium sulfate. And so they used the barium sulfate as a contrast dye to look at people's guts.
Will we have one of these on a quiz on Tuesday?
Probably yes. 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 Should I be more confident? Yes. You will have one of these on the quiz on Tuesday.
Oh my goodness. You see now the grades are gonna go.
You already have the concepts memorized with the equations.
No, it would be one
Give us the
where
equation already.
the products are written out. Not the product. The reactants are written out.
And
You have to
break
switch them.
Oh. So we don't have to like see the text
No.
and try to write it.
No. And so we're mixing barium chloride and sodium sulfate. What is the formula for barium chloride?
BACL.
BaCl2, and it's aqueous here, plus sodium sulfate, which is what? Na2SO4. And that is aqueous. What is that going to yield?
Barium chloride.
Barium sulfate. That one is given to us. Plus what?
Sodium chloride.
Sodium chloride, which we know is aqueous. Barium sulfate. Aqueous, solid. Question basically tells us it's solid. If you looked it up on the solubility table, it would point you to the fact that it's insoluble. We're going to put solid. So this question says write balanced molecular, ionic, and net ionic equations for this reaction. It says balanced. Before we start breaking this down, we need to balance the top one. Is it balanced?
No.
No. I have 2 chlorines there and 1 there. So let me put a 2 there, and then that balances sodium at the same time. Is that balanced?
Yep.
Yes. Now what do I have to do?
What's that in the parentheses behind sulfate?
There?
Yeah.
That's an S for solid. So I'm going to break it down. What does this become?
Barium ion.
Barium ion plus 2 chloride ions. It is not Cl2. These 2 chlorines are independent of each other. There's just 2 of them. So once you dissolve it, one can go this way, one can go that way. And so we have 2 chloride ions. So the 2 becomes a coefficient. Then I get 2 sodium ions plus 1 sulfate ion. Yields, what does that break into? Doesn't. It's a solid, so it doesn't break down. We get barium sulfate solid plus sodium ions. How many? 2. We still get 2. There are 2 times 1, 2 of them. Over here, there was 1 times 2 gives us 2. So we have 2 sodium ions plus how many chlorides? 2. So because we balanced the top one, as long as we carry all the numbers down to the second row is already balanced. We don't need to go back and rebalance that. Next step is the net ionic equation. What do we have to do to figure out what the net ionic equation is? You can either find out what made the precipitate, or you can cancel them out. Okay? If we cancel them out, what are the things called that we're canceling out? Spectator ions. What are the spectator ions here? Got chlorine and what? And sodium. There's 2 chlorines and 2 sodiums over there. There are 2 chlorines and 2 sodiums over here. Barium and the sulfate become part of a compound, and so they do not cancel out. So all we do is we copy down what is left. sense? See what I mean? It's not hard, it's just a lot of steps. It's a lot of work. So in this case, it specifically says to write the ionic equation. So you're not able to just say, this is the solid I made, but let me figure out what the net ionic equation must be. Okay. Changing gears a little bit. How many slides are left? I didn't, okay. I was thinking that the oxidation reduction was in a separate set. Okay. So we're going to change gears a bit. When we have a reaction, any reaction, whether it is combustion or a single displacement, double replacement, synthesis, or decomposition, there is an energy change that goes with it. There is always an energy change. We're going to talk more in depth about energy changes in another lecture, but we're going to touch on it today. If you burn something in the combustion reaction, the energy change is very obvious, right? It's hot. If you mix barium chloride and sodium sulfate, the temperature may not change perceptibly, but it is going to change. It just may be so small that you can't tell. But with every reaction, there is an energy change. In this reaction, heat is being released. The heat is being released and it is absorbed by whatever that flame is near. Whether it's your food, whether it's the beaker sitting on top, whether it's your arm that you accidentally reached across it, the heat is coming from the reaction into the surroundings. Okay? So when we talk about these reactions and energy changes, we have two compartments. We have the reaction and the surroundings. The surroundings are everything else, whether it's right next to it or it's the planet Mars. Everything except the reaction is the surroundings. Not only do chemical changes have energy changes, but every physical change also has an energy change. If I break this marker, is that a chemical or a physical change? Physical change. But I had to put energy into it to break it, right? So every change, whether it's chemical or physical, has an energy change that goes with it. And if the energy changes in a reaction, there's only two places it can go, up or down. Right? We have names for those. In an exothermic reaction, exothermic reactions lose heat. An endothermic reaction gains heat. And we draw these energy diagrams to show what happens over time to the energy in a reaction. So in this case, on the x-axis, we have time going from left to right, the beginning and the end of a reaction. On the y-axis, we have the amount of energy in the reaction, with low energy down here, high energy down here. So in an exothermic reaction, the reactants start here. This is just sort of a subjective place. There's no actual units here in this graph. But the reactants are here. Because it's exothermic, the products have to be lower. Exothermic reaction, the reaction gives off heat. It releases heat. So the amount of heat in the reaction goes down. And so it goes down and ends up the products down here. In an endothermic reaction, the reaction takes in heat. So the amount of energy goes up. So the reactants are at the bottom and the products are at top. In an exothermic reaction, which direction is the heat going?
Down.
In or out?
Out.
Out. So do you think an exothermic reaction feels hot or cold?
Oh wait,
Hot. it's kind of, it doesn't match what you probably think of first. Exothermic reaction, the heat in the reaction is going down. And so your first thought might be it's going to feel cold. But remember that your hand is not the reaction. Your hand is the surroundings. And so if the heat comes out of the reaction, it's going into your hand. And so your hand is absorbing the heat. If your hand absorbs the heat, you feel hot. In an endothermic reaction, the energy in the reaction goes up. Is it going to feel hot or cold? Cold. Why?
Because it takes in heat.
It takes in heat. Why does it make it feel cold?
Takes it away from your hand.
Exactly. That heat has to come from somewhere. Your hand. If I have an endothermic reaction occurring in a beaker, and I put my hand on it, it's going to suck the heat out of my hand into the reaction, and the temperature of my hand is going to go down. And so I am going to feel cold.
So we're looking at ourselves, not the reaction.
If you're thinking about what the temperature is, or does it feel hot or cold, that's the key. You're thinking about you, your hand, or a thermometer. If you put your hand on something and it feels hot, you certainly know that the thermometer temperature is going to be going up in that thing. The thermometer is the surroundings, just like your hand. In an exothermic reaction, the energy will come out of the reaction into the thermometer, making the temperature on the thermometer go up. Most chemical reactions are exothermic. Burning something is exothermic. That's why burning things continue to burn. The first little bit burns, it gives off a bunch of heat, and that bunch of heat makes the part of the log next to it catch on fire. And then that releases heat, which makes the part of the log next to that catch on fire. Can you think of an example of an endothermic reaction?
Yeah, like old ice.
That is a endothermic process, but there's not a chemical reaction. So that's outside of this class. That's physics.
But like when you go to the gym and you're working out, you get running or something.
That's evaporation, or
Well, your body.
well,
temperature rises.
your body temperature is rising. Why is your body temperature rising if you're exercising? Because your cells are burning, they're oxidizing, they're metabolizing things. That's a reaction. The reaction is in the cells that releases heat, makes your body hot. Is that exothermic or endothermic? That's exothermic. If I walked out in the hall and I slipped on a banana peel and sprained my ankle, what would you do?
Laugh. Sorry. Sorry.
What would you do?
Actually, if you're all right.
Ask me if I was okay, and if I said, yes, I'm okay, but my ankle hurts,
Put ice on it.
put ice on it. What if there was no ice around, but you had a first aid kit? What might be in that first aid kit?
One of those things that he.
One of the instant cold pack.
Oh.
So in those cold packs, there's two reactants that are separated together. There's usually a little packet of a liquid in there with a powder. But the liquid is in a little bag, so it's not touching the powder. If you squeeze the bag, it breaks open, and you mix the powder in the liquid, you get a reaction that's endothermic, and so feels cold. When you put it on your ankle, it sucks the heat out of your ankle into the reaction to make the reaction go, and your ankle gets cold. The hot pack is the same thing, except it's exothermic. There's two things that when you mix them, they release heat to make whatever your hand warmers hot. So this is burning of hydrogen. Hydrogen plus oxygen gives water and a whole bunch of heat. call it, we'll pick up here next week. And so the oxidation reduction part will not be on Tuesday's quiz, but it will be on the next Tuesday's quiz, because we're going to talk about it in the lecture next week.
I thought next Tuesday, the next Tuesday after this, we have a test.
Oh, no. We do have a,
It's not next.
It's not this Tuesday, yes. Oh, so you're right. So it'll be on that exam, but it won't. Does that make sense?
So what's on the next quiz?
The next quiz will be what we covered on Tuesday, plus what we covered today. Not oxidation reduction reactions.
And that'll be on the test.
Oxidation reduction reactions will be on the exam.
Will they be on Wiley, or will it like, how will Wiley work?
They will be on next week's Wiley.
Oh, okay, like you change the question?
Yes.
Do we have something similar to what we will have in the quiz in the Canvas homework?
The quizzes are generally similar. They test the same ideas as the Canvas homework,
Okay.
but they are not.
It's on, yeah.